Okay, we'll do an example problem. It's example 4.11. It's a big problem. It has rather 4 sections, but anyway, we'll do one by one. A 100 turn closely wound circular coil of radius 10 cm carries a current of 3.2 amperes. A 100 turn closely wound circular coil of radius 10 cm carries a current of 3.2 amperes. A. What is the field at the center of the coil? B. What is the magnetic moment of this coil? And further information is given. The coil is placed in a vertical plane and is free to rotate about a horizontal axis which coincides with its diameter. A uniform magnetic field of 2 Tesla in the horizontal direction exists such that initially the axis of the coil is in the direction of the field. The coil rotates through an angle of 90 degrees under the influence of the magnetic field. So, C is, what are the magnitudes of the torques on the coil in the initial and final position? Then D, what is the angular speed acquired by the coil when it is rotated by 90 degrees? The moment of inertia of the coil is 0.1 kilogram meter square. Okay? Anyway. It's a big problem, example problem. As I said, just 4 sections A, B, C and D. Then we'll do one by one. First, what is given? Example 4.11. A 100 turn closely wound circular coil. So, the number of turns in the coil is 100. It's closely wound circular coil of radius 10 centimeters. So, radius is 10 centimeters, which is 0.1 meters. That is also given. It carries a current I of 3.2 amperes. Then what's the first one? The first one is, what is the field at the center of the coil? So this is like that. So the coil is like this. So it's closely wound, it has 100 turns. It's 100 turns coil. And 100 turn coil. So they want you to find B at the center. So that's A. So the part A is this. What is B at the center? So we know the expression, right? We know the expression from your previous videos, that it is equal to N times mu naught I by 2R. Okay, so we've done that. We found the magnetic field B due to a circular coil at a point on the axis, right? And when it is the very center, then that becomes mu naught I by 2R, and that is for 1 turn, and for n turns it will be n into mu naught I by 2R. So that is, it's very simple. So that gives you n is 100 and mu naught is 4 pi into 10 power minus 7, I is 3.2 amperes, and divided by 2 times, this is 0.1, radius is 0.1. Okay, so if you do that, we are going to have approximately 2 into 10 power minus 3 Tesla. So it will be 2 into 10 power minus 3 Tesla. Let's see if it makes sense. Okay. Pi is 3.14 and this is current is 3.12. So 3.14 into 3.2 will become approximately 10, right? 3.14 into 3.2. So we know that pi squared is approximately 10. So 3.14 to 3.14 is 10. So 3.14 into 3.2 is roughly 10. So this becomes 10. Okay, so 10 power 3, 10 power minus 7. So that will become, the whole thing will cancel and then it will become 10 power minus 3. There. Okay. So then what happens here? So that is going to be okay. So this is going to be 2. So 2 into 10 power minus 3. Okay. So I think so 2 10 power minus 3, then 0.1 is going to 10 power minus 4 is what you will get, I think, yeah. Okay, so I hope I've done the problem properly. I think you should get 2 in 10 power minus 4 Tesla, not 2 in 10 power minus 3 Tesla as given in the textbook. So 4 pi 10 power minus 7 is 100, so 10 power minus 5 is what you will have, and then 3.12 into pi, so that will become 10. So 10 power minus 3, we are going to divide that by 2. So 2 and 0.1 will go up. No. Oh, this one, okay. So this is 10 power minus 1, right? Okay. 10 power minus 1. So this is 10 power minus 2, I should suppose. Okay. I hope I've done it properly. As a 2 10 power minus 2 Tesla is what you would get. But then the idea is simple, like it's a straightforward application of the formula. So B naught is equal to 10 into mu naught I by 2R. So mu naught is 4.10 power minus 7, I is 3.2, and 2 into R is 10 power minus 1. So if you do it like this, then yeah. No. Okay. So, okay. Let's do the second part, B. The magnetic moment of the coil is what is asked. So, what is the magnetic moment of the coil? We know that magnetic moment M is given by NAI or NOI, right? NAI or NIA, what you want to call that. So that gives you N is 100 and then A is pi R squared. Pi R is 0.1, so 10 power minus 1 pi R squared. I is 3.2, right? Okay. Here also, so this is 10 power minus 2, 100, it will cancel. And so 3.14, 3.12, so that is going to be equal to 10. 3.14 to 3.12. So 10 ampere meter square. Yes, this is ampere meter square. Number of turns will not have anything. So the unit for magnetic dipole moment is ampere meter square. So that is the B part of it. Okay. So then you can also find the direction. Suppose current is flowing this way, it's like this, right? So direction will be into the board. M direction will be into the board. Suppose the current is flowing in this direction, then M direction will be out of the board. I mean, that is not given, so you don't have to worry about the M direction. They have not told you in which direction the current is flowing in the coil. So this is how you do the second part. But now the third part, C. But before C, they have told us something. So what have they said? They said this. The coil is placed in a vertical plane. So it's a vertical plane. it's a vertical plane, and is free to rotate about a horizontal axis. Okay, the coil is placed in a vertical plane, so there is a horizontal axis, it is free to rotate about this axis. Okay. So it is placed, it's like this. You have it's vertical plane, so there is a horizontal axis you got. Then it is free to rotate about this horizontal axis. Okay. So the vertical plane is this. So it's a vertical plane. So there is a horizontal axis. It is free to rotate about this axis. That is what is said here. Okay. Axis which coincides with its diameter, that's what we saw, right? So this is a vertical plane, it is free to rotate about a horizontal axis which coincides with its diameter. A uniform magnetic field 2 Tesla in the horizontal direction exists such that initially the axis of the coil is in the direction of the field. Okay. A magnetic field of 2 Tesla is existing, it is along the horizontal axis. In the direction of the field, axis that initially exists in the direction of the field. The coil rotates through an angle 90 degrees under the influence of the magnetic field. Okay, so then what are the magnitudes of the torque torques on the axis of the coil in the initial and final position? So that is the question. Okay, now so how do you do that first? So first of all, C is the torque is given by M cross B, okay, or it is equal to M B sine theta. Okay, so initially so what is going to happen is the question. Suppose B is in this direction, B is in this direction, B is in this direction, and you have area like this, right? So your M will be in this direction initially. Okay, so B is in this direction, and the current is the M should be in this direction, right? So if it flows like this, the current flows like this, then B must be in this direction. So M cross B. Then it will start rotating. It will start rotating about that axis, right? So M cross B. So that is initially be 90 degrees, and so the torque can be calculated like this. What is M? M is 10, and then B is 2 Tesla into sine theta, which is equal to sine theta is 90 degrees, sine 90 is 1. So you're going to have 20 Newton meters. 20 Newton meter initially. But then once it has turned, and then once it has turned 90 degrees, and it will coincide with the B. We just saw that, right? Initially it is like this, B is like that. When we did that loop thing, B is like this, B is like this, and it could be like this. And then when it comes like this, turns and then it comes like this, then this can coincide with B. In that case, sine theta will be 0. Okay, so this initial torque would be this, and then the final torque is equal to same MB sine theta, MB sine 0. So it becomes 0. See, in your textbook it is given wrongly. They say the initial torque is 0 and then the final torque is 20 Newton meter. That cannot happen. If the initial torque is 0, then how would it even start rotating? Okay, so that cannot happen. So you have got the order wrong in your textbook. So the initial torque is 20 Newton meter and then the final torque is 0. So I want you to make note of this. Because the initial torque is 0, how would it even start rotating? Okay, so that cannot happen. Okay, fine. So that is done. And the fourth part. What is the fourth part? What is the angular speed acquired by the coil when it is rotated by 90 degrees? Once it is rotated by 90 degrees, what would be the angular speed of this? Okay. So what do we know first? We know the torque is equal to I to alpha. So torque is the force equivalent in rotation, right? F is equal to ma. So torque is equal to I alpha. I is the moment of inertia and alpha is the angular acceleration. So this is a mass equivalent in rotation and this is the angular acceleration. So this is a force equivalent in rotation. So torque is force equivalent in rotation and moment of inertia is a mass equivalent in rotation. So tau is equal to I alpha. Okay. But what is tau? Tau is mb sine theta, right? So tau is mb sine theta. Can I equate these two? So then I will say that I alpha is equal to mb sine theta. But what is alpha? Alpha is actually d omega by dt, right? So the angular rate of change of angular velocity is alpha. So I can do the same thing here. So that would be I into d omega by dt is equal to mb sine theta. Okay. So what can how else can I do this? How can I manipulate it? Well, let me take this. So d omega by dt can be written as d omega by dt into d theta by d theta. Okay, I am multiplying by d theta and dividing the by d theta. Why am I even doing it? Well, you see, I got theta here, but what I got here, I got dt. You see, it's difficult for me to integrate this, right? I need to express theta in terms of t. Only then I can do it, or I should do some other manipulation. Okay, so that is what I am going to do here. So this is going to be equal to, I am going to redo this now. I am going to do d omega by d theta into d theta by dt. So this d theta by dt is at omega at the time. So I can say that d omega by dt can be written as omega times d omega by d theta. The same. Okay. I can bring it here and then put it in here. So that is going to be I is equal to, instead of d omega by dt, I am going to say omega d omega by d theta is equal to mb sine theta. See, now it is much easier. Why? Because I can take d theta there and then do an integration. So I can say I omega d omega is equal to mb sine theta and d theta. Okay. Okay, once you get this, then it is very easy for you to manipulate this equation. Okay. let me just get this. Omega d omega is equal to m b by I, and then sine theta d theta. Okay. So now what is going to happen? See, this is going to go from a zero angular velocity to a certain angular velocity. Okay, so I'll call it as W f or omega f. Okay, so I'm going to integrate it, right? So I need to integrate it now. So it will go from, I integrate this. This will go from 0 to omega f. So that is omega d omega, and that is equal to this m b by I. These are constants I can take out, and then I need to talk about the angle. Okay. So what's the angle now? The angle, okay, initially B was like this. So B was like this, right? Sorry, okay, it was like this. B was like this. So what happened? This was 90 degrees. Okay? So this was 90 degrees. Then it will again rotate, right? It will rotate now. So as it rotates, then this will become, it will go from 90 to 180 degrees. Okay? Because 90 degree rotation, right? So you start from 90 degrees and then you go to 180 degree rotation. So that is going to be equal to sine theta d theta. So this will give you, so omega squared by 2 to 0 omega f, that is equal to mb by I. You got minus cos theta, then you have 180, then 90. Okay. So what is going to happen now? So this will give you omega f squared by 2, and that is equal to m b by I minus cos 180 is minus 1, minus of minus 1 is 1, then minus cos 90 will be 0, so that is simply 1. Okay, that's all. So this term will give you just 1 there. So from this you can find omega f. So your omega f is simply, take it there, 2mb by I square root. And then put in those values. So this is 2, m is 10, then b is again 2, and then I is 0.1, right? I was 0.1. The moment of inertia. Okay, this is not current, this is moment of inertia. So it is 0.1, so 10 power minus 1. So I take it up, so this will become 10 squared and square root. So out of 2 2's I'll get 2, and then out of 2 10's I'll get 10. So my omega f is equal to simply 20 radians per second. So that's the answer. So my omega f is going to be 20 radians per second. Okay, so let me repeat this. Let me try to explain this little further because it may confuse you. Let's see like what we have done in this part. Okay, we know that tau is equal to I alpha. We say tau is the rotational equivalent of force. Okay, so F is equal to ma in linear motion, and rotational motion tau is equal to I alpha, where I is the moment of inertia and alpha is the angular acceleration. So that was one equation. I tau is equal to I alpha, and tau we know from here is tau is mb sine theta. At any point, at any angle theta, then tau can be found as mb sine theta. Okay, so I alpha is equal to mb sine theta, but alpha is again rate of change of angular velocity. So alpha is d omega by dt, because we want to find omega, right? So I need to express alpha in terms of omega. So that gives me d omega by dt is equal to mb sin theta. Can I integrate it straight away? No, I can't, because this is in theta, this function is in theta, but I am going to integrate it with time, so that won't work. How can I integrate a function of angle with respect to time? I can't do that. I need to either convert the theta into time as a function of time, or I have to do other manipulations. I have to somehow convert t into theta or theta into t. That's how I can do it. So I do the same here. So I take d omega by dt and I multiply it by theta and then divide it by theta. Then I get d omega by d theta. So I get d theta by dt here. So but d theta by dt is omega anyway. So omega d omega by d theta is equal to d omega by dt. So I come here and then substitute that here in terms of in the place of d omega by dt. So I get mb sin theta like this. So now I omega d omega will give me mb sin theta d theta. Now I can integrate, because this is a function of theta and I am going to integrate it with respect to theta. So that makes sense, right? So now once I get this, I manipulated omega d omega is equal to mb by I sin theta d theta. So you are when I'm going to integrate it, I'm going to go from 0 angular velocity to some angular velocity, final angular velocity omega f, right? So I go from 0 to omega f of this function, and this function I'll start with 90 degrees, then there is a 90-degree turn, so I will start from 90 and then I'll go to 180 degree. So exactly that's what I do here. So 90 to 180 sin theta d theta. So when I do that, then I get this expression, and after that it is simply a question of substituting the values in this equation, and that will give me my final angular speed, angular velocity. So that is 20 radians per second. So this is how you do this problem. Okay. Hope this is clear to you. Okay. It's not very easy to do, but you can. You need to think about it a little to do this. Okay, now let's talk about some parallels between magnetic dipoles and electric dipoles. We just discussed one aspect of it. We said the torque due to an electric dipole was given by this expression. Torque was equal to P cross E, and in the case of magnetic dipole, the torque experienced by a magnetic dipole in an external magnetic field, I'll call this, was given by magnetic dipole moment cross the external magnetic field. Okay, so this is one analogy that we've already seen, and let us see if we can see a few more analogies between the electric dipole and the magnetic dipole. Okay, let me talk about the field, the magnetic field set up by a dipole. Okay, along its axis, we saw that, right? We took a circular loop, of radius r, current I, and then we set along this axis at a distance x, okay, at a point P along the axis. We need to find the magnetic field B, and that was given by this expression. This B was equal to, let me just put this one, okay, the mu naught I r squared by 2 times x squared plus r squared the whole power 3 by 2. Okay, we derived this in one of our videos. Okay, let's see, let me consider a case where this distance is much greater than the radius. Okay, my case is this. I have a small circular loop, but then I'm finding B at a far off place from there. Okay, so along the axis. So if x is much greater than r, then I can ignore this. R square can be ignored, and what happens to this expression is this: B is equal to mu naught I r squared by 2. I can ignore r squared because x is much greater than r. So x squared to the power 3 by 2, that gives me simply 2x cubed. So that is B. So the point is, we find the magnetic field due to the circular loop, the magnetic dipole, at a point along the x-axis, and it is very far, and this x is much greater than this r, then B will be reduced to this, be approximately equal to this. Okay, I am going to do something else now. Okay, I have got r squared now, I have I there, but what do I know? I know that m, the magnetic dipole moment of this dipole, m, the magnetic dipole moment is equal to I into A, right? Or NIA. N in this case is 1. Now m is equal to 9. N in this case is 1 because I am taking only one turn, one loop. Okay. So I into A. A is the area of this loop. Okay, I have got I there, r squared there. But what's the area of a circular loop? It's pi r squared, right? Okay. So let's see if I can multiply this by pi and then divide this by pi. Then what does it give me? It gives me mu naught I pi r squared by 2 pi x cubed. Okay. So that becomes B is equal to, what is pi r squared? That is A. So mu naught IA, area of the loop, by 2 pi x cubed. Okay. So what is IA? IA is simply m, because n is 1 anyway. So that is m, right? So that gives me mu naught m by 2 pi x cubed. And if I multiply this by 2 and then divide that by 2, then it gives me mu naught 2m by 4 pi x cubed. So remember this? Does it ring a bell? You see, when we found the the electric field due to a dipole, electric dipole, along its axis, we got this expression. Remember, an E, electric field due to a dipole, along its at a point, so x, along the x-axis, we got this expression. We saw mu naught 2p divided by 4 pi r cube. That's what we got. You see, you get the same thing for this. So, if you take a dipole, magnetic dipole, the magnetic field along the axis, okay, is very similar to the electric field due to an electric dipole. Okay, so you see 2p by 4 pi r cube. You got mu naught. Sorry, this one 2 4 pi epsilon naught into r cube. You see, you got mu naught 2m by 4 pi x cube. So this will also be falling off 1 by 3. So this was 2p by 4 pi epsilon naught r cube, and now this is mu naught 2m into mu naught by 4 pi into x cube. You see the same a similar structure is there. So likewise, we found this along the axis. Okay. Along the equatorial plane, like at a point on an equatorial plane, we found that to be E was equal to P by 4 pi epsilon naught r cube, right? At a point on the equatorial plane. Equatorial plane. So we found this. So an analogy of this, again you have a magnetic dipole and not along the axis but somewhere here along the equatorial plane, here, this place. Suppose this is a magnetic dipole. Okay, this expression is for a point along the axis. But what about a point here? What about a point here? Okay, that's along the equatorial plane, right? Equatorial plane. So it's like, so for this you will have something like this. It's equal to m, so mu naught m by 4 pi x cube. Okay, on the equatorial plane, and the plane itself, perpendicular to this. So here, either here or here, at some distance x. So this is what you find. You see, it's very similar. So let me do a comparison here. E along the equatorial axis, along the axis was 2p by 4 pi epsilon naught x cube. Okay, and B along the axis was same 2m by 4 pi x cube, and then you got mu naught here. Okay, so this mu naught by 4 pi, it's 1 by 4 pi epsilon naught. So that's the two different constants, but the structure is similar. And likewise, equatorial plane, E along the equatorial plane, I'll say it was equal to P by 4 pi epsilon naught x cube, and B, something like that here, is equal to mu naught m by 4 pi to x cube. So you can find the similarity between this and that. Okay. So P is analogous to M, or I should say M is analogous to P, and then B, the magnetic field, is analogous to E. Okay. And the equations are very similar. So if you know one equation, then you should be able to do the other equation. If you know the equation for the electric field, then you can find the equation for the magnetic field. So they're very, very, very similar. Okay. But there is one difference though. See, in the case of an electric dipole, you had a clear positive charge and then a negative charge. There are two charges. You could separate them. I can take the positive charge out and then I can take the negative charge out. But in the case of a magnetic dipole, you cannot separate north pole and then the south pole. They always occur in pairs. Okay? So magnetic monopole does not exist. Electric monopoles exist, and there is a negative charge, electron. There is a positive charge, proton. They are separate. But there is no north pole alone, and there is no south pole alone. Whenever you take a magnet and then break it, you will always have a north and south pole together. Okay? You take a magnet, cut it into two pieces, then I have north and south, and north and south here. And take that and then cut it into two more pieces, then again I have north and south on each of them. I can never separate a north pole from a south pole. There is magnetic monopoles do not exist. But then electric monopoles, they do exist. You have electron, purely negatively charged, proton, positively charged. So electric monopoles exist, but magnetic monopoles do not exist. Okay, but that's the only difference. But the moment you talk about dipoles, whether they are electric dipoles or magnetic dipoles, they have similar characteristics. Okay, you have a magnetic dipole moment, you have an electric dipole moment. Okay, you have magnetic field set up by magnetic dipole, you have electric field set up by electric dipole, and the equations for these two are very similar. And then you have torque experienced by a magnetic dipole in an external magnetic field, and then you have torque experienced by an electric dipole in an external electric field, and then those equations are also very similar. Tau is equal to P cross E, or tau is equal to M cross P. Okay, so they're very similar the moment you talk about dipoles. Okay, hope this is clear to you. There is another interesting phenomenon which is called as the magnetic dipole moment of an electron. Okay, an electron. Okay, it's part of an atom. How would you get the dipole moment of an electron? Okay. Let's see. Think about it for a while. Okay, so you have nucleus, it's positively charged, and then you have an electron going around it. Okay. So this is an electron going around. Maybe it's moving this way, B, this direction. So R is the radius. So this is, what is an electron? Electron is a charge, okay? Electric charge, and it is moving, which means there is current because of the movement of an electron. And if there is current, there would be a magnetic field. So there would be a magnetic field created by the electron, by the moving electron. Okay? Notice this. And this electron is also moving in a loop. Okay? Whenever you have current moving in a loop, then you are going to have a magnetic dipole. Okay? So a moving electron is a magnetic dipole, because a moving electron is a moving charge is current, and current creates a magnetic field, and the moving charge is in a loop. So the moment you have something in a loop, you are going to have a magnetic dipole. Okay? And if you have a magnetic dipole, then you must be able to calculate the magnetic dipole moment of the dipole. Okay? So what is that? Magnetic dipole moment M is equal to NIA or NEI. So but this is only single loop, so this will become IA. Okay. So the magnetic dipole moment of an electron is simply IA. Okay. I'm going to use a different symbol for this. It's going to be mu L. Okay. Magnetic dipole moment of this electron. Okay. That is mu. That is equal to I to A. So to find this out, I need to find the current. Okay. So what's the current here? How do you find the current? Current is simply charge per time. So this is E is the charge, and it makes one round. Okay, it comes back again, right? So what's the current then? E by the time it takes to complete one circle. Then how do we find the time? Well, 2 pi r is the length, is the distance it travels, and v is the speed with which it travels, right? So the time, or this is T, capital T. So this time is simply 2 pi r divided by the speed with which it is going to go. Is that clear? Okay. So now 2 pi r by v will give me time. Then what's the current? So the current is simply E by 2 pi r by v. So that gives me EV by 2 pi r. So that's the current. Okay. But which direction the current will be? The current will be in this direction because electron is moving in this direction, but in the current direction it should be this. Because electron is a negative charge. So if electron moves this way, then you assume that the current is moving in the opposite direction. Okay. So that's the difference. But then I is, the magnitude of the current is EV by 2 pi r. And what's the magnetic moment? Okay. M is equal to I into A, or I should say mu L, right? Mu L is equal to I into A. So that is, what is my I? I is EV by 2 pi r, say found there. But A will be the area of the loop, right? The area of the loop is pi r squared. So pi r square. So pi and pi will cancel, then r there. I'm going to have EV r by 2. So that is my magnetic dipole moment, magnetic moment, shortly magnetic moment of the electron. Okay. Well, I can do some more manipulation. I got r and v. So what I'll do now is this. What I'll do now is this mu L. I'm going to EV r by 2. Multiply this by m, mass of the electron, by mass of, divided by mass of the electron. Okay. So it won't change, right? But then I can do this. I can combine this. So what is it? M or V? M or V is the angular momentum of the electron. R and V, right? That's the angular momentum of the electron. So which is represented as L. It is equal to E and then L by 2me. So this is angular momentum L. Remember? L is equal to RmV, R into P. Okay? R cross P, right? So that's what I'm trying to say. This one. Okay, but this is the magnitude. But what about the direction? What about the vector quantity? So you see mu L. Which direction is the same? Okay, I is doing this. Oh, it's out of the board. Okay, but which direction is this? Which direction is L? L will be R cross P, right? Okay, this is L is actually equal to R cross P. So R is in this direction, R is in this direction. Momentum of the electron will be in this direction, right? Mass into V. That's my P. P is mass into V. Velocity is in this, velocity of the electron is in this direction. So R cross P inwards. Okay. So L direction is inwards. It goes into the board. But M direction is mu L direction. The moment, the dipole moment direction, mu L, that is out. So L direction is inwards and M direction or the moment direction is out. Magnetic dipole moment direction is that. So if I take this as a vector, then I will say that this negative of E by 2me to mass of the electron. It's not m into e, it's mass of the electron, subscript. Then L direction. So I have to take L direction, L with the direction, and then the opposite to the direction is what I have, my magnetic moment pointing at. Okay, so this is the vector quantity. Okay. Purely from, again, let me go back to the scalar quantities, okay, the magnitudes around. So this is vector representation. Let me go back here. If I go back there, then mu L is equal to EL by 2ME, and then I can have mu L by L. Bring the L there, and I get E by 2ME. Okay, that is the ratio of magnetic dipole moment to the angular momentum. Okay, L. So that is E by 2ME. So this is called as gyromagnetic ratio. Okay, so this is called as gyromagnetic ratio. This is a constant number. Why is it a constant number? So easy, right? Okay, so what is E? E is 1.6 into 10 power minus 19, and this is 2 into, this is 9.1 into 10 power minus 31. Okay. So it's roughly 10, okay, so 10 power minus 30, then when it goes there, 10 power 11, so 1.6 by 2, and then 16 by 2 into 10 power 10, okay, so roughly it's approximately equal to, or rather it is equal to 8.8 into 10 power 10 coulomb per kg. Coulomb per kg. So it's a constant number. So this is called as a gyromagnetic ratio. So that which is the magnetic dipole moment divided by the angular momentum of the electron. It's a constant number. Okay. Well, okay. So this is fine. So what else can we do? But can you find ml now? But then see, when you find ml, you need to require you require the velocity and then the radius and all that, right? So only then you can find this equation looks like that. Only with that I can find the magnetic dipole moment of the electron. But then in Bohr's atom model, he says this. One of the Bohr postulates this. The angular momentum is going to be an integral multiple of h by 2 pi. That's what he says. Which means, let's see, Bohr's atom model gives you this value for L. L is equal to n h by 2 pi. See, the electron is moving in this orbit. So when it is moving in the closest orbit, the ground state, okay, then you call this n value will be 1. And when you excite an electron and it goes to a different orbit and then goes around the nucleus, then n would be 2, and then n can be 3, n can be 4. Because on all those different orbits, you will have different angular momentum, right? The velocity will change, orbit will change, radius will change, so a different angular momentum. But at a minimum, when it is in the ground state, at a minimum, when it is the ground state, this n will be 1. Okay. Next, h has a value, the Planck's constant, 6.3 into 10 power minus 34. So that is there. Okay. So you have Planck's constant, and then 2 into pi. So this, using this expression, I can find mu. So what is this? Mu, angular magnetic dipole moment is equal to E into NH by 2 pi, NH by 2 pi into 2 mu. Okay, or I can say that E by 2 me, right? E by 2 me we already found. That is 8.8 into 10 power 10 into nh by 2 pi. nh by 2 pi. nh by 2 pi. Okay? So if you put the values for this, at a minimum I said n will become 1, right? So if I take the minimum value, mu L minimum, the minimum, n will become 1, which is the closest. Okay, so since it's the closest, you see, we'll do this. 8.8 into 10 power 10 into n is 1, h is 6.63 into 10 power minus 34 divided by 2 into 3.14. Okay, so this gives you this gives you the value 9.27 into 10 to the power minus 24 ampere meter square. Okay, so this value, this is called as Bohr magneton. Okay, so this is the magnetic dipole moment, the minimum magnetic dipole moment of an electron in an atom. Okay, the ground state, this is what, this is the magnetic moment that each electron will have. Okay, so that this is called as the Bohr magneton. And apart from this magnetic dipole moment, an electron will also have a spin dipole moment. Okay, it's a spin dipole moment. Spin. But what is this? This is called as the orbital moment. Orbital magnetic moment. Okay, because it is orbiting around the nucleus, right? It's orbital magnetic moment, which is equal to 9.27 10 power minus 24. But apart from this orbital magnetic moment, an electron also has a spin dipole moment. I mean, it doesn't mean that electron is spinning or something. It doesn't have an axis to spin. Okay, it is not a, it's a fundamental particle, and it doesn't have an axis or a size or something to spin about. Okay, but then we call that as a spin dipole moment. Okay, and that will have the same value as this. That is in addition to this orbital dipole moment. Okay. In addition to orbital magnetic dipole moment, an electron will also possess a spin dipole moment that has the same value as this. So it has both. Okay. But what you have calculated here is the orbital dipole moment of an electron. And in addition to this, it also has the same amount of spin dipole moment. And that is considered to be, that's a cause for some of the magnetic properties of the magnetic properties of some of the materials, like iron and other materials. They have the magnetic properties, right? And the reason for the magnetic properties of those materials is considered to be the spin dipole moment, okay? The spin dipole moment. Okay? So what you need to understand is that an electron which is orbiting around the nucleus will have at a minimum this 9.27 10 power minus 24 ampere meter square dipole moment. Okay, this is called as the Bohr magneton. This is the orbital dipole moment. And in addition to this, it also has a spin dipole moment that's of the same value. Okay. But we are not going to talk about that. Okay. But this is a very simple way of calculating the dipole moment, the orbital dipole moment of an electron. Okay. What we need to understand is that if you take an atom, the electrons which are going around the atom, they behave like magnets now. This magnetism is everywhere. Even at the atomic level, you find the magnetism. So because we will see the values and then how to derive it at a fundamental level. Okay. So the important things are gyromagnetic ratio mu L by L, which is E by 2 me, and then Bohr magneton, this value, and then this is the orbital dipole moment, and apart from this, electron also possesses a spin dipole moment, which we are not considering here, but it has the same value as this. Okay. Hope this is clear.